they work at how to, so they want to describe how it's going, the evolution of Loma stars. So before I will talk about this work, I want to start with some history. So in 1995, we all know that there was first exoplanet, extrasolar planet was observed, and also brown dwarf was observed directly. And parallelly, this observation of star-forming regions was so improved that one can imagine, image forming stars with a circumstellar disk, so which they that time called protoplanetary disk, because people expect that planets will be formed in that circumstellar disks. And so this year was some kind of beginning of new era for astronomy today, and lots of astronomers pointed their mind on how to link stars, brown dwarfs, planets, and these disks. So 4 different objects, but very similar in one hand side and very different in the other hand side, and how to link them, what is the theory, what is the model for that. And these objects required a stellar evolution model which could give accurate masses, because it was very crucial to distinction between stars and brown dwarfs. We know that in brown dwarfs there is no nuclear reaction, and stars, how they differs, what mass is for one brown dwarf and what is for stars should be. And also precise age and mass determination was required for young objects which have these circumstellar disks, and also accurate knowledge of parent stars for extrasolar planets was required for that. And this time, lots of observers start to observe this kind of objects, and there was lots of work done before the paper what I will present was published. So lots of observations and lots of theory on these objects, and particularly in the Loma stars. So Loma stars actually are stars which are less massive than our sun, but because they are stars, they should be massive than the hydrogen burning minimum mass. So here are the parameters of these Loma stars. If you can see, they are quite compact objects, and but they also quite cool objects comparing to other stars, to sun-like solar-type stars and stars in the main sequence. And modeling of these very low mass stars required these 2 things. One is a correction to the non-ideal effects in equation of state for the inner part physics of star, and also for it required a derivation of accurate models for star atmospheres, because when they have effective temperature less than 500 kelvins, the atmosphere of stars becoming to quite cool, and the absorption becomes to be the main contributor to the star. Yeah, absorption of molecules becomes to be the major contributors. So before that time, there was gray approximation of star atmospheres, which means that atmosphere absorb in all wavelengths of light similarly, like the same absorption in all wavelengths. But when the atmosphere becomes to be cooler, then and molecules forms there, and there should be there was done new model of atmospheres for stars, which called non-gray, where absorption of these different molecules was taken into account. So in this work, authors presented new calculations of evolutionary models of low-mass stars, which used two things. So first is theory of improved stellar interior physics, which they did 1 year before this paper, and it based on these 5 points, which is improved equation of state for hydrogen and helium in these stars, enhancement factor of nuclear rates for these low-mass stars, and also updated opacities of molecules and other elements from Iglesias and Rogers, and also this last generation of non-gray atmosphere models. So why atmosphere was so important here? Because it is so atmosphere model is define outer outer boundary condition of the inner physics of star. So it was very important to know which model of atmosphere to use there, because it changed the results of evolutionary models quite significantly. And also, so what did they actually find? Accurate boundary conditions between this inner part of star and outer part, which is atmosphere. And also, they used new, for that time was new non-gray atmosphere model called Next Gen. So, and doing these calculations based on that points what I mentioned, they derive effective temperature and central temperature relationship, which you see here on the x-axis logarithm of central temperature, and in y-axis effective temperature of stars for given masses of stars. And we see here two models. So the model was calculated for solar type, solar metallicity for 5 gigayears, and here it's a solid line. And what we see here with dashed line is that gray atmosphere models, which was did before. And we can see it here significantly changes in the slope of evolutionary track here also. So that means that atmosphere models which used before these gray atmosphere models overestimated the effective temperature, and they give wrong luminosity for these stars. And this model was quite improved in this case. And also they calculated the mass and effective temperature relationship, which is very, very important for the observers to derive mass from the observation. And here with the solid lines is present model, and the other lines are different models which they calculated before this publication. And this time they calculated for solar, solar metallicity, and here for low metallicity stars. But also he find that for the stars which have mass less than 0.6 solar mass, the mixing length parameter, which was some main parameter of this model, is not like the varying of this mixed length parameter is not so sufficient for stars, for models with mass less than 0.6 solar mass. But it comes to be important when the masses are up at this limit. So they also calculated several models, few models which where they want to represent solar properties of the sun using this helium abundance and length mixing length parameter 1.9, and so this helium abundance. But other models was done with mixing length parameter equal to 1. Then these models gave also mass magnitude relation, which is also very important for observers, because we cannot derive really mass from observation if they are not binaries or or if they are not triples or binaries, etc. But for the single stars, for the stars which are not binded so strong, we cannot say what mass they have. But from this theory, from the model which calculated here, they show good consistency with observations. So the points here is observational points from Henry and McCarthy. And also, they derived color magnitude diagram from the models, which also have quite good agreement with observations for stars with lower metallicity. For example, here calculated model was compared to globular cluster 47 Toucan, and you can see that the observational points fits very well with calculated model. But for the open stars, there was some uncertainty. So calculated models were too blue than observed ones. But this was one negative side of, not so negative, but just some minus of this model. But when they look at on color magnitude diagram of field stars in infrared wavelengths, they also fitted very well with observations, and that uncertainty which they have for optical region here, they said that it could be because the metallicity of the star is so like Titan O absorption lengths are very important in the optical lens, but when we observe it in infrared lens, there are lots of a fraction of molecular hydrogen is more than this metal oxides, and it comes more consistent with the model and consistent model with observations. So, because this model had very good agreement with observations, it was used even up to days very most of observers, most of astronomers used that. And also they compared observations of disk stars and their models. And also here we see that it fits only in the upper region, but it has some uncertainty, and model is too blue for the comparing to observations. But so this work was done in 1998, and after that they also worked in this topic and had lots of publications. And in 2015 was published one more work which continued these models, and then their model was more consistent with observations. How we see here, the red lines are newer calculations of evolutionary models, and black line is the present paper in 1998. And what they did here was two things. One is varying mixing length parameter, which was constant in the first paper, and also they used more they used complete line list of Titan oxide for this.
This variation of the mixing length parameter, is that a physical question, or is it just a parameter to fit this curves? Because this mixing length parameter is not really, it was always a fitting parameter, I think, to stellar models. So is it now based on this variation based on a physical ground? I don't know.
So it's important when you calculating inner physics of the star and this convection of star, and I'm not sure why it mostly, yeah, please.
So the mixing length parameter is not really physically motivated at all, but you need it if you want to treat convection. And we use this 1.9 is used because we calibrated with the sun, but you don't really expect all evolutionary stages to have the same thing as the sun, but it's the best we have.
So here it's a free parameter then. And
Yeah, so that's,
okay.
so for example, in the first paper they fixed this parameter and it was from the beginning up to end, but in the recent work they was varying it. And they also using this completed line list of Titan oxide, they could derive more correct evolutionary model for color magnitude diagram in optical region. So so as I said, it was because when we observe it in infrared, there is more fraction of molecular hydrogen have absorbed is a major contributor to absorption, but in optical wavelengths the metals are main contributors. So when they used this complete line list, they could derive a correct model. So for the conclusion, I would say that this model is still one of more realistic model of evolutionary models for low mass stars with low metallicity and solar metallicity, and it also mostly agree with observations, but and predicted optical colors were too blue in the first part of work, but in the recent work they could correct this. So thank you very much for your